Hello everyone, and welcome back to day 2, notes in our probability and statistics chapter. Today we're talking about theoretical probability and the ideas between simple events and compound events. So probability, is the measure of how likely an event is to occur. We refer to the set of all possible outcomes as the sample space. And for equally likely outcomes, the theoretical probability of an event, the probability of event E, is just the ratio of the number of favorable outcomes to the total number of outcomes. In other words, it's a fraction of what do I want over what are all the possibilities. So let's say a jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? So I'm looking for the probability of red, and I'm looking for how many reds there are, 32, over how many total there are, 60, reducing that to a probability of 8 out of 15 that I will choose a red marble out of that jar. Let's look at another example. A letter in the word restoration is randomly selected. What is the probability of selecting a vowel? Well, probability of a vowel is going to be the total number of vowels, 1, 2, 3, 4, 5, over the total number of letters, which is 11. Okay, simple events, pretty straightforward. Probability of one event happening, it's my desired outcome over all my possible outcomes. Now, the complement of an event is going to be the probability of that event not happening. So the complement of an event is the probability of the event not occurring. I do this by taking 1 minus the probability of an event, probability of event E, because the sum of all the probabilities in the sample space is 1, or like 100%, and so that's going to be the difference between 100% and the probability of whatever I want. So for example, the probability that it will snow tomorrow is 7 out of 20. What is the probability of not snow? Well, that would be 1 minus the probability that it will snow. And so that would be 20 out of 20 minus 7 out of 20, which would be 13 out of 20. All right, so let's look at number 10. 2 dice are rolled. What is the probability of not getting doubles? Well, that would be 1 minus the probability of getting doubles. So what's the probability of getting doubles? Well, out of a total of 36 rolls of the dice, right? 2 6-sided die would be out of 36. I could get 6 rolls that are doubles, right? 2 1s, 2 2s, 2 3s, etc. And so I am looking at 1 minus 6 over 36, which would be 30 over 36, which would be divided or reduced down 5 over 6. So I have to find the probability of my event and then 1 minus that probability. Now, with compound events, as opposed to simple events, I'm looking at the probability of 2 things happening. So I've got independent and dependent events. Independent events, as the title suggests, is when the outcome of one event does not affect the outcome of another. So probability of A and B happening, that it rains and we have spaghetti for dinner, is just the probability of A times the probability of B. One event does not influence the outcome of the other. However, in dependent events, I have a situation where the outcome of one event does affect the outcome of the other event. The probability of it raining and us going outside, let's say, is going to be the probability of A times the probability of B after A occurred. And we'll talk more about that in a second. For example, a die is rolled 3 times. What is the probability of getting 1s on each roll? Well, here's a situation of an independent event where one roll doesn't affect the other. It's 1 out of 6 because I'm taking one die and rolling it 3 times, and the probability of getting 1 each time doesn't change based on what the previous outcome was. And that is 1 out of 216 times. Now, in terms of a dependent event, a coin is tossed, then a day of the week is selected. What is the probability of getting tails, and then a day starting with the letter T? Okay, so I'm looking at the probability of getting tails, which would be 1 out of 2, times, now the probability of getting a day starting with the letter T, I believe that would be Tuesday or Thursday, right? So that would be 2 out of 7, and that would be a total of 2 out of 14. Right, let's do a couple more here. Let's talk about, these are all independent events. Where a bag contains 8 red crayons, 14 purple, 6 yellow, and 4 green. A crayon is selected, replaced, and then another is selected. Find each probability. Okay, in this case, I'm starting with purple and then yellow. So I'm looking for the probability of getting a purple. That's 14 out of a total of 32 crayons. And then the probability of a yellow. The outcome here of getting a purple doesn't affect the outcome of a yellow, because if I put the purple, my original crayon, the purple one, back, I'm starting with a brand new full set of crayons each time. So the total number of crayons resets to 32. So I'm looking at a total of, when we reduce this, 21 over 256. Okay, now when I talk about dependent events, where the outcome of one is affected by the outcome of the other, using the same example from above, so we'll look at the number of crayons, I'm assuming now that once a crayon is selected, it is not replaced. Now the outcome of one does affect the other, so find each probability. Now I want a probability of a yellow and then a red without replacement. So what I'm looking at is the probability of a yellow, which is 6 out of 32. Now the probability of a red after yellow has already been selected. Well, there are still going to be 8 red crayons, but now there are only 31 crayons the second time I take a crayon out. And what I'm looking at here is a reduced fraction of 3 out of 62. Let's do another example here. If a card is drawn from a standard deck and not replaced, what is the probability of choosing a heart and then a spade? So the probability of a heart and then a spade. So the probability of getting a heart, there are 13 hearts out of a total of 52 cards in the deck. I am not putting that first card back in, so I'm going to end up with 51 total cards still in the deck, and there are 13 spades, in the deck. And so when I multiply this out, I get, 13 times 13. Delete that. 13 times 13 is 169, and then I'm multiplying 52 times 51, and that is 2652. So I'm looking at 169 over, what did I say, 2652? Over 2652, and that reduces to 13 over 204. Both of those are divisible by 13. Okay, you are on your way to homework 2, theoretical probability. The homework for tonight is to do the odds, please. So must do the odds, should do the evens as well.